right, Friday morning, weekend's almost here. Anything good come up over the week? Looking at linear algebra. Where are we at today? Looking at more solving equations or getting into linear regression work? Just starting, that's fine. Getting started. Anything good coming up as you're getting started? Questions about like readings or homework? Not yet. All right. Check in. Small group today. Just the hardcore numerical methods people. Okay. Yeah. Just like reviewing like meeting. Yeah. Okay. Yeah, just okay. Anything stand out? Okay. Okay. So because you said that is going from 100 to 1110, that start at 100, go to 1100, then you it would have been something like, yeah, stop. Really, like part of this is just recommend it's all because of the equation. So kind of taking a look at, we have a matrix equation, and if our force is pushing straight down, are we getting results that kind of make sense? When it's negative, this is kind of a review of statics. That means that the vector that you drew is in the opposite direction. And that makes sense because the way that it's drawn here is all like, if P is positive, it's a compressive force. If P is negative, it's a tensile force. So this is saying P1 is actually pointing in that direction, that it's pulling that bottom one apart. So it makes it, at least I think it makes sense to say that that is negative versus that force like in newtons. So the bigger the force, the more negative P1 gets. So by the time we get to 1,000 newtons, P1 has like 140 newtons of tensile force inside that bar. So then the other part, and so one of the reasons that I ask you to solve like every 10 newtons on this step is that I wanted you, it's kind of a lesson of like, look, if you have a linear problem, the answer is always linear. So 10 times more force, 10 times more tension, 100 times, also 100 times, because we're solving that problem of like A, P1, P2, R equals 0, 1, 0 times F. So the solution is always, whatever that F multiplier is, that's how big the solution will change. Kind of cool. It's nice when things work out like that linearly. If we started looking at like different angles, then that would be a different problem. Like now we have sines and cosines in there, but for these big like magnitude change, if the magnitude is changing of our right-hand side force vector, our left-hand side solution is all going to change by the same magnitude. And that's nice because I could also say, what do I want to do? Let's do like every 50, like that. If I have one solution, I have all of those solutions that I just asked for. Here, like in the first, all the dots that I just plotted, I kind of spaced them out so that I have more room between them. All those dots are solving every 50 newtons versus just plugging in and saying like, all right, well, let me solve for the 0, 1, 0, and then just multiply that answer by whatever magnitude of force I need. Ends up being the same exact result, whether I go through and solve it every time or just take the one solution and scale it. Cool. The question that nobody asked, there's the answer. So in this problem where we have like a 6x6 matrix, where we're trying to get the LU decomposition and then use that to solve for that P123 R123. So we have all these things that we'll get solutions for. All we're really looking for is just like how much tension or compression in bar 1 is there. At least the force, tension or compression force. So if you go through, if we get the LU decomposition, if we use that LU from SciPy, it does some partial pivoting for us to make sure that when we do, so the Gauss elimination doesn't give us an issue. So I can use those, and in the reading there's a forward and backward substitution method. It kind of goes through 2 for loops to first solve the forward substitution, then solve the back substitution. So I could use that and say solve LU, and I think I give it L and U, and then I think, did I call it B? Sorry, I gotta go back up and check. Yeah, so my right hand side is B. If I want to have 100 newtons, then I'll say B times 100. But I also need to, since I use partial pivoting, then I also want to pivot those output of B. So I want to take that out, that right hand side, and multiply by that pivot transposed, because we're trying to solve this problem, AX equals B, where I have matrix X, unknown vector, matrix A, unknown vector X, known vector B. That's my linear algebra equation. So I'm changing it to P L U times X equals B. But I can get rid of that pivot on this side by saying P transpose times P. So that all becomes just the identity. And then this side is now going to be P transpose times that B. So it's just taking those the values in that right hand side and rearranging them to match the new LU solution. And sure enough, I get some answers. They seem right. For 100 newtons, pushing at a slight angle, there's less kind of tension in that number here. For 100 newtons, I get 15 newtons of like tension force in that bar 1. So you can use LU, you can use this solve LU, or the equivalent is Y. So printing out those 2 different steps. One is just using solve twice, and when you have lower upper matrices like that, solve is going to solve it pretty quickly. I actually don't know what the time difference would be between the 2. Let's try it. So solve LU is just using forward-backward substitution versus linalg.solve twice. It's actually a little faster to just use the linalg solve. Not much faster, because it is the same problem, like it's doing the same thing. But is it always faster? 52, 40. Yeah, always a little faster. I think because the solve method uses like C++ functions to run through the for loops rather than having Python. So Python for loops in general are pretty slow. Use them anytime you want because we're engineers, like we're mechanical engineers. The goal is get some answers with some results. And then if you're running into issues of like, this is taking minutes to go through this analysis, then get somebody else to write it in C++ for you, or Fortran or something, I don't know. Or dig into the documentation, write it yourself. It's all open source. You can always add new methods, new libraries. Yeah, but I wasn't sure which one would be faster. Yeah, that's good. That's actually what it should be. Yeah. It is, the problem is that two solve. You could compress them and you could say that X3 doesn't or you could say X didn't or X5 didn't. They all, anytime you all compress and you move them anywhere. Yeah. That one should work. At least for by hand. It does give me out. So it doesn't help. Yeah. Yeah, let me because this is yeah, I specifically set up the give you those documents so I can move them through and I think this stuff is not expected. So is it supposed to return this error? It's supposed to. So and it's actually it's not an error, it's just kind of a warning, right? All right, so let's jump back up to so I have this matrix of big A, the 6x6 A matrix, and then 6 unknown kind of reaction and internal forces with 6 known applied forces. I'm gonna use just a naive Gauss method and just try to shove it all in there and say like, all right, figure it out. Tell me what the answer is. So here I'm defining A, I define B, it's all fine. So now I'm gonna say Gauss naive of A and B, and they'll multiply by 100 to give us. It does give me an answer. Like it's telling me like, okay, here's the answer, but there's some warnings because you're dividing by 0. And in general, Python doesn't like divide by 0 because it just doesn't know what to do with the answer. So I end up with all these values of like negative infinity and not in numbers, and all of my outputs of like the solution X, like all those reaction forces and internal forces are all not a number because I'm dividing by 0. So let me go back to my original set of equations and take a look at this. So if I'm trying to do like matrix math on this to do Gauss elimination, my first step is taking row 1 and subtracting it from row 2 so that I can get rid of that 1. But my first term is a 0. So in order to get like 1 minus 0 times something equals 0, the answer is infinity. The only way, I mean, it doesn't even really give you an answer. That's why we get so many not a numbers. And we can kind of see that if we had like a simpler example, 0, 1, 2, 3, x and y equals 1 and 5. So if this is my set of equations, I can kind of look at this and immediately know, all right, 0 times x plus 1 times y is 1. Because I'm not a computer. I'm not going to like naively try to do Gauss elimination. But for the computer, if I'm doing naive Gauss, I'm going to say 1, all right, infinity times row 1. So row 1 stays the same. So then 2 minus 0, or minus 2 over 0, and 3 minus 2 over 0, x and y, and then 1, and then, oh yeah, let's do the augmented matrix, right? 1, and then 5 minus 1 over 0, like that. I guess this should be this is the output from my like naive Gauss elimination, is that I now have like 0s and 1s. But a much easier way to solve this is just, there was no reason that this had to be equation 1 and this had to be equation 2. So let's do some partial pivoting. We say 2 and 3 still times x and y is all 5 and 1. So I'm taking that augmented matrix and kind of flipping it, and then say 0, 1. And now it's already in an upper triangular matrix. Gauss elimination is done just in that one step. So how do we do that here? If you want to use that LU decomposition, like I could use that pivot matrix and multiply it by A and get it into a new shape. So since I already did that, I could say like P transpose times A, P transpose time, or I guess it would just be P, is it P transpose? Or is it just P times A? I think P times A. Yeah, just P times A. P times B. Pretty sure. So it'll rearrange the equations just to get it into something that will work for Gauss elimination. Or I could ignore that and go back up and manually say, well, this doesn't have to be row 1. This is going to be, row 2 is going to be row 1 now. And really I'm switching this 0 with a 0, but that's okay. And now when I try Gauss naive, it gives me same result as using that like pivot matrix that I just got before. Yeah. The pivot will have like a couple extra row switches. Like if you look at it here, if it's diagonals of 1, then all the rows are exactly where they started. As you see, the ones move to different spots. It's saying like row 1 and row 2 were switched, and then also like row 6 and row 4, or row 3, row 4, row 6 and 4 were switched, something like that. Kind of shuffling things around. Or you get the same answer, whether you just switch the first 2 or switch all of them. That's like the manual process of just look at it, do the partial pivoting yourself, switch those rows. Yeah, I get for 100 newtons, -15 Newton So 15 Newton tensile in bar 1. $75, $60, $45. I don't know. Do I have the right angles in there? 75, 30, 45. 75, 30, 45. Beta is 30. Yep. Alpha is 75. Yep. Beta is power 4. I don't know. Anything else come up in the last couple of minutes? Maybe this is just too easy. Seen it all before. Yeah. 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 Yeah, that's it. Like once we set up like all of these constants and the matrix, then we can use Gauss naive, we can use linalg.solve, but we end up with like, all right, here's the positions. Basically 1, 2, 3, 1, 2.5, 1, 2, 2.5, about 3. No, in this case, we're just looking at like a static equilibrium kind of problem. Yeah, someone else brought up like, oh, I think we've seen this in vibrations, and we couldn't like if we set that up, it would still be a linear algebra problem, but then we'd be looking at like what are the natural frequencies and what are the magnitudes associated with those different vibration modes. Um, and if you like that kind of stuff, then module 5 gets into like how you would set up that kind of equation, because that would be in here. Pull this up. Derivatives, keep it steady, some good vibrations. So if we had like two masses, kind of like this, I'm just going to scroll down. We could look at like different types of vibration modes for those two masses, and then using, and it's still just a linear algebra kind of problem, but we can figure out like how much of the vibration is mode 1 versus mode 2, and then combine them all for an answer. Yeah, you get, but it's the exact same kind of setup. It's just now we're pulling out that natural frequency and then mode shapes instead of static solution. And we know it's static here because everything is equal to 0. Like weight plus spring force is all equal to 0. And in general, if it's static or a steady state kind of solution, it turns into a linear algebra problem. And if it's like a time varying problem, it's still linear algebra, but now you end up with like a linear set of differential equations. Sometimes non-linear, you can have nonlinear, but some kind of set of differential equations versus just equations, multiple equations, multiple unknowns. Cool. Nice way to end the day. Sneak off into the weekend. And we'll be back Monday. Monday is Veterans Day, so if you are celebrating a veteran, then please tell them thanks for their service. If not, then I'll see you here. All right. Have a great weekend.